Hello everyone, and welcome back to this series on single variable calculus. Today we're going to be continuing our exploration of integration and talk about another application that integrals can help us solve. In particular, the realm for which this application actually belongs to the realm of physics. But there are several different applications out there in the realm of physics for which calculus can be involved, both differential and integral, but I want to focus on something that a lot of people can kind of get an idea around, or might even already have some idea on how to solve it without using math. So what I want to do is I want to consider some flat object in two-dimensional space. So let's assume that we have this region here, and let's assume that it has some area. All right, so we have some region. Let's assume this region, let's call it R, and that's obviously a subset of two-dimensional real space. And let's assume that we're interested in asking, if I want to balance this point, or balance this region about a point with your finger, assuming uniform density, where would you balance it? Well, you might guess that maybe the center of mass, is what we call it, is probably located somewhere around here. So we can say call this mx, and we can, for example, call this point right here my. So this point, or this center of mass, is where you would balance that surface on your finger, and it wouldn't topple over due to gravity. So the question is, how do we find mx and my in this particular picture? Right, so how to find mx and my. So for the realm of single variable calculus, we're going to be making a couple of assumptions. The first is actually a physical assumption. So let's call this assumption number 1, is that the object, has uniform density. So what do I mean by uniform density? So let's actually consider a circle in two-dimensional space. Here, that's going to be of uniform density, and here, which is not going to be of uniform density. So if uniform density, which I'm going to abbreviate by Greek letter rho, so if this is uniform density, you should be able to balance this about this particular point. So this would be mx, and this would be my, and the center of mass for a circle should be the center of that circle. But if it's not uniform density, for example, if density, let's say, decreases from left to right, so in some sense it's extremely heavy here, not as heavy here, even less heavy here, and it's lightest over here, so it decreases from left to right, so then you would probably expect the center of mass to probably be located somewhere towards the left, right? So probably mx would be here, and my, if it's uniform in the vertical direction, still would be the center y coordinate of that circle, right? Just the center of mass x coordinate would be shifted towards left, where it has larger density. But in this particular calculation, we're going to be assuming the former, that the density is uniform for this particular object. The second requirement, so assumption number 2, is an assumption that we need in the realm of single variable calculus. Once we get to multivariable calculus, this assumption will no longer be needed, but the assumption is going to go as follows. So this area can be represented as the area bounded between two functions of a single variable. So what exactly does that mean in the graphical sense? So what we're going to have, as usual, we're going to have some region, but we're going to have an upper bound. For example, let's call this, for example, f of x. We're going to have a lower bound. Let's call this g of x. And we're going to be considering the area on some interval a, b. And so this right here is going to be our region R. right? So this area or this region R is bounded between vertically two functions f and g. So what does this mean in terms of the left and right boundaries? So this means that the vertical linear left and right boundaries, and partially curved top and bottom boundaries. Right? So if you want a region whose entire boundary is potentially curved, then you would have to use, for example, multivariable calculus in order to solve that. Or you can use single variable calculus, but you have to be extremely more clever to sort of set that up. So now we know the problem that we seek to solve. That is, we're trying to find the center of mass for this object, right? So we're trying to find mx and my, assuming that the density of this object is completely uniform at any point in this particular space, and the north and south boundaries per se are represented by some functions of, say, some variable x. Now that we know that the problem that we're going to solve, now let's see if we can formulate how to solve it. So let's bring back a formula from basic chemistry that you probably learned some time ago. So what is the relationship between density, mass, and volume? Well, you should know that the density is equal to the quotient of mass and volume for an object. And what we're going to be focused on is the center of mass, so we just need to solve this equation for m. So we find that mass for an object is going to be equal to density times volume. So this is going to be one of the equations that we're going to be pretty much building our equations from. And keep in mind, in 3 dimensions, what is the volume for a cube or a rectangular prism? You should know that the volume will be equal to length times width times height. And in 2D, it's not really called volume, but it will just reduce to area, which is length times width. Right? And why do we really care about cubes and rectangles? Well, we can approximate the area of any region between two curves with rectangles, right? That's the idea of Riemann sums, and where sort of integrals or Riemann integrals get their formulas from. In 3 dimensions, what we're eventually going to discuss in the multivariable realm is we can approximate the volume under a surface with a bunch of cubes or rectangular prisms, and it pretty much follows the same exact idea. So what we want to do is use the 2-dimensional area representation to approximate mass in 2 dimensions. So what would that look like? So that means mass is going to be equal to density times area in 2 dimensions, which is going to be equal to density times, and since we have framed this from the area between 2 curves, this is just going to be the area or the integral from a to b of f of x minus g of x dx. And here we're assuming that our picture pretty much looks like this, right? So here's our area, our top function f, our bottom function g, with base points a and b. So this is going to be our equation for total mass, right? So this is the total mass of that region. And now we need to figure out the center of mass. But before we do that, I want to sort of introduce some terms that are commonly used in this conversation. The first one is called the moment of x, and the second one is called the moment of y. So what exactly is the moment of x, and what exactly is the moment of y? I'm going to give you very basic definitions, and we'll get into the more theoretical and why we define them this way in more of a statistical mechanics type of realm. So the moment of x is defined to be equal to the balance measure around the y-axis, and the moment of y will be the balance measure around the x-axis. So pretty much what we're looking for the center of mass that will balance the surface at a particular point. So we need both x and y balance points. And since the moment of x represents the balance measure around the y-axis, we're going to be calling this my. And the balance measure around the x-axis, we're going to be calling this x. All right. So once we have this, now we can start to build these equations. So what will be my? So my will be equal to the weighted average. So this will be the weighted average of the change in x representations from our definition. And keep in mind, delta x will be equal to f of x minus g of x, at least in principle what they're representing. And that's obviously going to be with respect to x over our region, in particular a to b. So that means, using this idea and definition, my will be equal to the density times the integral from a to b of our weighted average, so x times those differentials, f of x minus g of x dx. So that gives us our moment of x, my. And now let's figure out how to find mx. So mx is just going to be equal to the median position with respect to our vertical components. So this is going to be equal to, once we actually work that out, so mx, so pretty much we're trying to find the median of the vertical components with respect to density. So we have density times the integral from a to b of f of x plus g of x divided by 2. So what exactly is this? Well, this is the median of vertical positions over that particular area. So times f of x minus g of x dx. Now keep in mind I have f plus g and f minus g, so I can distribute those and get a difference of squares, and you can find a nicer representation for mx. So we have that mx, or our moment of y, will be equal to density times the integral from a to b of 1/2 of f of x squared minus g of x squared dx. All right, so we have mx and my. So these are the moments of x's, or the moment of x and the moment of y. So now what we're going to do is we're going to define the center of mass. So the center of mass, which I'm just going to call Cm, is going to be equal to our moment of x, which is my, divided by our total mass m, and then our moment of y, which we called mx, divided by m. So this is how you find the center of mass for a two-dimensional region, assuming uniform density. Let's work out a numerical example just to make sure we know how to use these formulas. Now keep in mind, the derivation of our equations for the center of mass is not completely physics-based, it's kind of intuition-based, so it's not necessarily a formal proof, as we need to sort of, figure out a couple other physics relations to formally prove that. We'll get into that in the future when we start actually doing some physics or formal physics, but for now we're just going to take these as axiomatic with those explanations or quote-unquote derivations to be quote-unquote valid. So if they are valid, how would we find the center of mass for a region that's described as the region R bounded between these two linear functions, plus or minus 0.2 x plus 2 on the interval 0 to L. So I'm using this L as a sort of degrees of freedom to give you a little bit more flexibility on these calculations. So what exactly does this region look like? So we have an intercept of y is equal to 2. We have one line that's going up and then the other line going down, right? And for some value on the bottom, for example, there is some number L that dictates what this region is going to look like. All right, so here's our region R, which obviously depends on L, and if we were to bisect this little angle, that obviously would be at y is equal to 2. So take a guess. Do you know the y-coordinate that will balance this particular region? You should be guessing 2 if this is, equally balanced for that top triangle and bottom triangle in terms of density. But where would the x be? You want to take a guess? And if you don't know how to guess, let's just use the formula and see what comes out. But it would make sense that the balance point in the y-coordinate should be 2. So hopefully that comes out correctly. So the first thing that I want to find is the total mass. So the total mass is going to be equal to rho times the integral from 0 to L of, again, f of x minus g of x. So this is going to be equal to f of x, our upper boundary, minus our lower boundary, negative 0.2x plus 2. And then we need to integrate with respect to x. So this is going to be equal to our density times the integral from 0 to L of 0.4x dx. And another useful thing to note is I didn't mention the density of this object because in some sense it shouldn't matter. The balance point should remain the same, right? It's just a little bit more heavier to hold with one finger if you have, so for example, a larger density. So what would this integral be? So the integral of this, so we're going to add 1 to the exponent and divide by 2. So that's going to be 0.2 x squared. And then we need to evaluate this as x goes to L and as x goes to 0. So what we get is the total mass of this is going to be equal to rho times 0.2 L squared. 0.2 L squared. Right, so what exactly does this mean? So the larger the density, the larger the mass, the larger the length, the larger the mass as well, right? But quadratically, the larger the length, the larger the mass. So now that we have our total mass, now let us find our moment of x, my, and our moment of y, mx. And then we can find our center of mass values. So what is the moment of x? So the moment of x, aka my, will be equal to rho times the integral from 0 to L of x times the difference of fx and gx. So again, that's going to be 0.2x plus 2 minus negative 0.2x plus 2. And then we integrate with respect to x. So this is going to be equal to our density times the integral from 0 to L. And then it's pretty much going to be the same integral as before. The only difference is going to be 0.4x squared instead of just x. So we're just going to divide that by 3 now. So we're going to have rho times 0.4 all over 3 times x cubed as x goes to L, as x goes to 0. I don't really like decimals and fractions, so I'm just going to multiply top and bottom of this equation by 10. So I'm going to have our moment of x, aka my, will just be equal to rho times 4 over 30 times L cubed. So that's going to be our moment of x. And then I'm going to do similar to the moment of y. So the moment of y, aka mx, is going to be equal to rho times the integral from 0 to L of 1/2 of the difference of the squares between these functions. So 0.2x plus 2 squared minus negative 0.2x plus 2 squared dx. And be very, very careful when you FOIL those, and make sure to distribute that negative, and don't forget that little negative there. But once you work out all that algebra, what you're going to have is the integral from 0 to L of 1/2, and then you're just going to be left with a lonely 1.6x on the inside. So please be sure to verify all that algebra in between. So keep in mind 1.6 divided by 2, so that's going to be equal to the integral from 0 to L of 0.8x dx. Increase the power by 1, that turns into 2. Divide by 2, that turns the coefficient into 0.4. So I'm going to have that mx will be equal to what? So that's going to be rho times 0.4x squared, which evaluates as x goes to L, as x goes to 0. So that means mx will be equal to rho times 0.4 L squared. So that gives us mx. So now that we have my, mx, and m, now we should be able to find our center of mass. So therefore, our center of mass will be equal to, so let's just recall the equation, so my divided by m, and then mx divided by m. For our equation, that's going to come out to my, which is rho times 4/30 L cubed, all over rho 0.2 L squared. And then we're going to have rho times 0.4 L squared, all over rho times 0.2 L squared. Notice that our rho's do cancel, So our center of mass does not depend on density. It being uniform is one of the primary reasons for that. And then we have a lot of cancellations. So notice that our y-coordinate for our center of mass doesn't change when we change our value of L, so that satisfies our original intuition. 0.4 divided by 0.2 is 2. That's another thing that was intuitive from the start. And then we have some nasty little fractions here, and our x center of mass does definitely depend on L. So what we have here is that Cm will be equal to 2/3 L, comma 2. Right, so the longer the length, the longer or the farther away our x center of mass coordinate turns into. So if we have our region, right, so let's assume that this is centered around x is equal to 2. And let's assume that this vertical length, let's assume that this here is 6. And then we have 4, and we have 2, and then we have 0. So what do I mention 4? Well, 4 is 2/3 of 6. So the center of mass is actually located right there. So there's our center of mass for this region shaded here. Right? So here I'm choosing L to be equal to 6 in case you haven't figured that out. Right? So therefore, if L is equal to 6, then our center of mass will be equal to 4, comma 2. And that's how you find the center of mass for a two-dimensional object whose region can be represented as a difference between two different functions in R2, and also whose density is assumed to be uniform. So I hope you enjoyed this fun little application of integration in the realm of physics. You might even want to sort of think about if density wasn't uniform, how would you factor that in to these equations? So I hope you enjoyed this video, and I'll see you in the next one. Take care.